Okay, let's dive right into this explainer and tackle a massive headache that honestly almost every AI developer is going to face eventually. We're talking about the vector database migration. So imagine this scenario, right? You've built a fantastic RAG application. It's working perfectly on a local embedded store. But now you need to scale. You have to move to a managed provider like QDRANT. And the absolute nightmare here is having to rewrite your entire core business logic. Your retrieval rules, your migration strategies, all your quality tests, just because you're swapping out the underlying database. It's painful, it's risky, and it just eats up weeks of engineering time. But today, we're going to explore how establishing a strict, contract-driven architecture through AI Fabric actually solves this whole mess. We'll see exactly how to keep your application contract completely stable and secure, even as the provider changes right out from under it.
So here's our quick roadmap for today. We're going to cover the managed provider shift, the vector boundary contract, collections and stable IDs, readiness and lifecycle parity, and then wrap up with how to avoid some dangerously incorrect architectures.
Starting off with Section 1, the managed provider shift, and moving to QDRANT smoothly.
Let's say we're looking at our Prod 07 release for a support knowledge assistant. We want to replace our previous vector database service with QDRANT, but, and this is a big but, we absolutely must keep our golden RAG test cases totally intact. So the crucial takeaway here is that your application services should never, ever import a QDRANT client directly into the business logic. Instead, they hit a substitution boundary. Think of the AI Fabric contracts right there in the center of this architecture, kind of like a universal travel adapter. Your core business code simply plugs right into that adapter. Then, when you actually deploy the application, a Spring profile acts as the wall socket, selecting the specific provider. Your application genuinely doesn't know and doesn't care if it's talking to a tiny embedded Lucene index on a developer's laptop or a massive, distributed, managed QDRANT cloud instance in production. The core meaning and behavior stay exactly identical. It's literally only the deployment capability that changes.
Moving on to Section 2, the vector boundary contract. We're going way beyond just similarity search here.
See, replacing a managed provider is about way more than just calculating nearest neighbors. It's about strict operational guarantees. AI Fabric's vector contract distinctly separates search filtering from scan filtering. A managed provider must safely preserve your exact match filtering semantics. And here is a massive security gotcha that catches so many teams off guard. If the underlying system cannot translate a requested tenant filter, it must never silently drop the filter and artificially widen the query. It has to fail closed. Think of it like a bank vault. If the security system can't properly read your keycard, it doesn't just, leave the vault door cracked open for everyone. It jams the lock entirely. This strict contract has to reliably cover everything from exact storage, updates and deletes, all the way to the crucial batch lifecycle operations that actually keep massive production systems running smoothly day in and day out.
Now, we have to talk about dimensions. Honestly, you'd be surprised how often this exact issue takes down production systems. Embedding dimensions are a strict physical storage contract. If your system is using a local ONX embedding model at 384 dimensions, you absolutely cannot write mixed vector sizes into a single collection. Upgrading to a brand new, powerful model with a different dimension size isn't just some harmless configuration toggle you can casually flip on a Friday afternoon. If you try that, the database will flat out reject the mismatched vectors and take down your entire indexing pipeline. You need a completely separate named collection or a highly controlled reindex procedure. AI Fabric acts as the strict bouncer here, making sure that when QDRANT collections are dynamically created, they strictly respect that exact requested vector size and cosine distance configuration.
Okay, Section 3, Collections and Stable IDs, focusing on operational isolation and entity mapping. Let's see how this all maps out in our actual data structures. It is absolutely vital to understand the difference between operational isolation and tenant authorization. A collection prefix is purely for operational isolation. It's exactly like putting your name on your lunch in the shared office fridge so it doesn't accidentally collide with someone else's meal. It keeps things organized, but that prefix is not security. Multiple distinct tenants, let's say tenant blue and tenant red, can safely live inside a single shared knowledge article collection. How is that safe? Well, because every single record carries approved metadata. Every retrieval request acts as a strict security guard, using verified tenant filters and application post-hit checks to guarantee that tenant blue never ever sees tenant red's data. And this brilliantly illustrates a true golden rule of RAG architectures. Stable application entity IDs must produce stable vector IDs. Think about the life cycle of a real-world document for a second.
When you update a billing article in your primary source database, your data sync updates the source projection under the exact same ID. If you were to generate a shiny new random ID for the vector on every single update, you'd leave this massive trail of highly dangerous, stale versions floating around as garbage in your vector store. An update has to precisely overwrite that exact logical point, and a delete must instantly wipe it out. If you don't aggressively enforce stable ID mapping, your RAG application is eventually and confidently going to hallucinate, serving outdated, forbidden, or downright incorrect information to your end users.
Section 4. Readiness and Lifecycle Parity. Basically, how you prove the migration is actually complete.
So let's say you migrated your data and you have the expected number of QDRANT points. Hey, that's a great start, but honestly, that alone is entirely insufficient. A provider migration is only fully complete when every single existing application behavior remains completely true and passes your automated quality contracts without a single modification. For instance, your Prado06 golden scorecard must pass without expected IDs shifting around. You have to definitively prove that tenant blue only retrieves blue's evidence. You have to prove that a trusted create command successfully and atomically writes both the source and the vector state. Look, if your access and lifecycle contracts don't pass exactly as perfectly as they did on your old embedded store, your migration isn't finished, it's broken.
Furthermore, just checking if your Spring Boot app started successfully, that only proves local process health, and that's just not enough in a distributed system. AI Fabric uses deep readiness diagnostics to prove native endpoint reachability and the actual state of your payload indexes. It validates the active REST or gRPC transport, ensures the collection shape matches your model perfectly, and verifies that your native metadata filtering is set up correctly in the provider. But here is the absolutely critical part. It must do this securely. Endpoint credentials and API keys must stay locked firmly in the runtime secret store. They should never, ever leak into your readiness output, your health checks, or your application logs.
We also have to fundamentally address durability and source ownership here. Yes, QDRANT stores durable provider state, but remember a core philosophy. Vector evidence is inherently derived and rebuildable. Your core application relational database is always the ultimate source of truth. Why? Because networks are incredibly flaky. A network response can drop right after QDRANT successfully accepts a write, or a source transaction might fail mid-flight. Because of this chaos, you absolutely need stable IDs, idempotent retries, and clean reindex procedures. This is exactly why, when we run our local Docker QDRANT tests, we mount a named volume. We want to rigorously exercise how the system handles durable, persistent state upon restarts, not just volatile happy path process memory.
And finally, Section 5. Avoiding incorrect architectures and the absolute necessity of visible failure.
If you run a release smoke test against an unreachable QDRANT endpoint, the indexing must fail visibly and loudly. Why? Because the evidence could not be written, and you need to know that instantly. The absolute worst thing your application can do here is silently switch back to a local embedded Lucene index, or even worse, fake a success count during a network outage. We call this hidden fallback, and let me tell you, it is an architectural nightmare for debugging. It makes your deployment dashboard look perfectly green and healthy while silently serving data from a completely different, outdated storage system. An empty index is fundamentally different from having insufficient context, and hidden fallbacks completely destroy your ability to tell those two scenarios apart when you are debugging a live system.
Let's compare these underlying approaches. An incorrect, messy migration binds your business logic directly to one single provider. It lazily injects QDRANT SDK calls straight into your REST controllers, or incredibly dangerously trusts a client-supplied payload as actual proof of tenant filtering. That severely weakens both your application's security and your ability to operate the system long-term. The correct architecture utilizes the AI Fabric boundary. It cleanly keeps all provider implementation details hidden, it derives tenant scope securely on the back end via the authenticated principal, and it runs the exact same deterministic lifecycle checks regardless of which database provider is currently plugged in behind the scenes. I want to highlight a crucial quote directly from the architecture guidelines here. A managed vector provider is valuable when it changes deployment capability without changing application meaning. That right there is the absolute holy grail of database migrations. Ultimately, AI Fabric makes that substitution boundary crystal clear. Your provider-native operations run quietly underneath, doing all the heavy lifting and scaling, while your portable lifecycle, access, quality, and readiness contracts remain firmly above them. This cleanly protects your core business logic from constant vendor churn and framework fatigue. So I want you to look closely at your own AI systems today and ask yourself a really hard question. Does your RAG architecture guarantee visible failure? Or have you accidentally hard-coded vendor lock-in behind a web of messy, leaky abstractions? Take a hard look at your architectural boundaries and your quality gates this week.
Thanks so much for joining me for this explainer, and keep building resilient, adaptable architectures.